a revision of the tutorial that I sent you earlier. We are going to have some discussion around how to solve some of the problems that were in that tutorial. And then if you're not able to finish that, then maybe we'll proceed on Wednesday. But my plan is that we finish that revision this week because it marks the end of our study, so that you have next week to prepare yourselves for the upcoming exams. So basically, we are only going to have our class this week. All right, so without wasting time, I see the quorum is already here. So I will just share my screen so we can proceed from there. So just give me a minute. All right. So this is the tutorial. I'm sure you have a copy. And so let's see if we can solve some of these problems. Now, I say that there are those problems that I really don't have to solve, because either they're in your notes or maybe it's there. You can easily find solutions to them, especially the first section on timers and counters. These are found in your notes. They're found in the book by Petruzella, and some of them are just, we've already discussed them in class. So I wouldn't want to spend much time on them, because I'm not probably going to even spend 2 hours in this class today because of other engagements that I have now. So I expect that we are able to solve any questions on the timers, question 1 to 6 on timers. If there is anything there that's really confusing or that you'd want clarification on, then you can ask. But I don't think, because this is just the basics of timers, I don't think there should be an issue with this. Okay, like asking applications what constitutes an on delay timer, what is a preset time, what timer does not maintain its elapsed time. So we know there's retentive and non-retentive, so you have to figure out which one is it. So I think the timers should not be a problem. The counters, 3 forms of PLC counter instructions, each one should know that. There are 3 counters: the up counter, the down counter, and the up down. State 4 pieces of information usually associated with the PLC counter instruction. Again, this is information that already is in your notes. You've encountered them. We say that whenever you actually you're drawing a counter, there are certain pieces of information that must be included. The name of the counter, what it does, the address, the accumulator, all this stuff. All right. So let me get to the gist of the matter, which is on ladder diagrams, because I know this is where probably quite a number are experiencing issues. So it's important for me to assist you to be able to solve these problems easily. Now, the question, if you look at it critically, you see that there's already a diagram there that's expected to start and stop a 3-phase electric motor. So in this diagram, you can clearly see that there is a reason why we already have the input field devices. So you already have the input field devices indicated there. And that's important, because when those are indicated, then they inform you of how you should draw your ladder diagram. And then, of course, there's the output field device there. Field. There's the output field device here, which is the coil that actually now starts the motor. So we are expected at this point to figure out some of the issues that come up when a ladder diagram is drawn. So we already know that the start push button usually is in the normally open position. That is when they're manufactured. The stop push button comes as a normally closed contact. You can see this is a normally open contact. This is a normally closed contact. And of course, the overload, the thermal overload, is also normally closed because it's meant to protect the motor from overheating. So this kind of scenario is put here to help you figure out the issues that exist with the ladder diagram. So there are several ladder diagrams drawn here, and we need to figure out where the problem is with each one of them. If there's a problem, we need to know for each one of them. So let's consider the first one. This is we've done a lot of ladder diagrams that assist us to start and stop a motor, that we know. So even the first diagram here is a very simple one. All you have to remember is that you have a contact here. You have a contact there for the start push button. Okay, and then you have another contact here for the stop push button. And then you also have another contact for the thermal overload. So we have a thermal overload here. Okay, let me just say overload. So those are the field devices. But now we are simply focusing on how the ladder diagram is drawn. Now, because of our experience before, the start push button here is normally open, so that when it is pressed, then it's meant to start the motor, or it's supposed to energize the motor. So it's connected to a push button, the start push button. So these ones are usually sometimes called, because we always call these physical devices, sometimes we call these physical devices because they're actually physical in nature. Then these ones, sometimes some books will call them virtual devices, because you can't really touch them. These ones really are just symbols that help us with the ladder diagram, and they are software, so we can't really touch them. Of course, and then you have your output, okay, out there for the coil, the motor contactor or the motor starter coil. So one, we have to identify what the problem is here with our the first ladder diagram. This should be a very easy one, especially having drawn several ladder diagrams that involve starting or stopping a motor. Now, we had agreed earlier that the start push button is always in the normally open contact. And so its virtual component is also in the normally open contact. So there's nothing wrong with the start push button. So that when it is pressed, then it gives you a logic 1, and therefore we get a logic 1 here. Okay, so we don't have a problem with that because it operates well. If you want to start a motor, you simply make contact on the physical start push button, and then that translates to a logic 1 on the virtual push button, the start push button, the normally open contact. So there's no problem with that. Number 2 is the stop push button. So you notice that the physical device, we have said this over and over again. This is a normally closed contact. And we have said that for it to operate properly, because then it means as it is already, it is passing logic. And because it is a protection mechanism, or it's a way to stop the motor, if it is pressed, then it's supposed to break the contact. So if it is pressed, it's supposed to give you a logic 0. So because it's a stop button and it's already in the normally closed contact position, you can see it means it's already providing you with a logic 1. Therefore, the proper way to connect is to have a normally open contact as the virtual contact. So the normally open contact, the push button, the stop push button, should be in the normally open position because it is already in the normally closed position. So that you just think about it, so that if somebody engages the stop push button, or if you press the stop push button, then you break the contact, meaning you give it a logic 0. And so this will get a logic 0 because it's a stop button. If it gets a logic 0, the motor will not be energized. The motor will not run. Okay. So that's why it's supposed to be, because remember, if we made them, and we've said this over the throughout the semester, if we, for example, made this a normally closed contact, if we decided that, okay, fine, let's make this a normally closed contact, so it's closed, and the stop push button already comes as a normally closed contact. So what that means that when somebody engages the stop push button, it gives you a logic 0. And so if you give a NOT gate a logic 0, you get a logic 1. And the logic 1 means now you've energized, you transferred 1 to the motor output. So therefore, it means that the motor would start running. So the stop button would start the motor if connected as a normally closed contact here and also here. So I think I cannot overemphasize this enough. We have discussed it several times. So the stop push button is in the correct position because the physical device is already in the normally closed position. So the virtual device, the virtual stop push button, should be in the normally open position. So that if somebody engages the stop button, it means it breaks the contact and gives a logic 0. And so the virtual device will take the logic 0 and transfer it to the output, which therefore means it will de-energize the motor, and so it will stop running. Okay, so this is a correct position. So we've agreed here, the start push button connected properly, the stop push button connected properly as well. The other one is the overload switch, the thermal overload switch. Again, this works in such a way that because there's a sensor on the overload switch here, if it senses a certain temperature beyond the threshold for the motor, then it's supposed to engage, and then the motor is supposed to stop because the motor windings might melt at higher temperatures. So exactly what that means is that it is also a stop push button, so that when it is engaged, it gives you a logic 0, which then is transferred to the motor for the motor to stop. Remember, for the motor to run, we need a logic 1. For it to stop, we need a logic 0. So this overload should contribute a logic 0 when it is engaged. As it is, because it's already connected as a normally closed, it is already providing a logic 1. So when it is engaged, when you press it, or when the sensor senses the right, the voltage, the temperature, the excess temperature, it should engage the overload, and therefore that would provide a logic 0. Now you notice here it's also connected as a normally closed contact. So let's say you've engaged the overload, it's supposed to break the contact, so gives you a logic 0. So logic 0 given to a NOT gate will give a logic 1. Logic 1 will start the motor. So clearly you can see that the biggest challenge here is, just like the push button, the overload switch should be a normally open contact. So this is where the problem is with this ladder diagram, that this should be a normally open contact. Why? Because the physical device is already in the normally closed position. So for it to work properly, then the overload switch is in the normally open contact. So we've done this several times in several questions, and we've seen that typically the physical device for the stop push button and the thermal overload switch usually comes as a normally closed device. So on the ladder diagram, we connect them as normally open contacts. So if you were to explain this, then you would explain that because we have the physical devices already are in the normally closed or come as normally closed contacts, then for the ladder diagram to operate properly, then we need to have the overload switch connected as a normally open contact, not a normally closed as it is. So this is where we have an issue, okay, with that ladder diagram. Because the idea for the overload switch is that when a certain temperature is exceeded, then it's supposed to break the contact here on the physical device. Breaking the contact means gives you a logic 0. So here I need to have a normally open contact so that when it gets the logic 0, it transfers it to the output so that the motor is de-energized. So that's what's expected. But if I put it as a normally closed contact, if I give it a logic 0, it will transfer a logic 1 to the output. And we don't need a logic 1 at the output because it's an overload switch. So the motor does not need to run when the temperature is exceeded, when the set temperature is exceeded. So I hope that is clear. Unless there's a question on it, you can ask me, because this is just a revision session. I am not teaching. Kama kuna swali on this, you may ask. Let me check if there's anyone who has put anything concerning that in the chat. But this one should not be a big issue, because it's a very simple it's a very, very simple illustration, because we've done it again severally before. So what to remember here is the connections between the physical devices and the virtual devices, especially for the stop push button and the overload switch. Let me move on to the next one. In the interest of time, let me move on to the next ladder diagram and see if there's any problem with the next ladder diagram. So this guy has decided to redraw this ladder diagram, but now you can see that he has decided that the push button sets the motor. Again, remember, this is a latching circuit. The first circuit here is a latching circuit, because you already know that this is latching. This is latching because we've taken the input and connected it to, the output is connected as an input, is branched out to the start button. So that is latching. Again, another way of achieving it is using the set reset mechanism that we have in the second ladder diagram. But now look at it. The push button, the start push button, is setting the motor, meaning it's supposed to energize the motor. Then the stop push button or the overload switch are expected to reset the motor, meaning to return its to de-energize the motor, okay, for that matter. So clearly this circuit is still appropriate, but let's identify if there's a problem with it. Now, if I press the start button, now actually the idea here is not really on the physical device or on the, but basically it's on the virtual section, because what I see here is that if the push button is pressed, it's supposed to set the motor. So because this is the set reset mechanism that we also discussed in class before. Now, this works. The first rung number 1 is fine, because typically if you're deciding to use the set reset mechanism, which is another form of latching. Now let's look at how we had agreed a ladder diagram should be read out. Remember, I'll take you back to the first case. We had said we can read this out as if, remember the Boolean expression for the ladder diagram, if the start push button or the motor input, here we have, and the stop push button and the overload switch, then the motor. So the condition for the motor to start is if the push button is engaged, or the motor input is already considered, and the push button is considered and the overload switch is considered. So you consider the position. So if, consider the state of the push button, or consider the state of the motor input, and consider the state of the stop push button, and consider the state of the overload switch. So then the motor position would be given. Okay, so that is it. So let's look at this ladder diagram. This one is if you engage the start push button, then you set the motor, which is to energize the motor. So that is fine. The second ladder diagram would be if you engage the stop push button, and because they are connected in series, we know that is and. Again, the overload switch, then the output. So the condition for resetting the motor, because it's a set reset network here, the condition for resetting the motor is if the push button position and the overload switch position is considered, then the motor is reset. Now, the biggest challenge here, if you can see, is this guy here. Because what this therefore means is if the controller or the processor will have to look at the condition of the push button and combine it with the position of the overload switch before it resets the motor. So the biggest challenge is here, and because typically we say that the push button should not be dependent on another device. Like the push button should be able to stop the motor independently. And the overload switch should also be able to stop the motor independently. But here, it requires us to have a combination of both the push button and the overload switch, meaning I must engage the push button, the stop push button, sorry, I must engage the stop push button, and the motor must have exceeded its working temperature for it to be reset. So it means, therefore, that the biggest problem with this ladder diagram is that it's considering that both conditions must be considered before the motor is reset. We must consider, the problem here is that this assumes that we must consider both the condition of the stop push button and the condition of the overload switch, which is wrong, because then it means that the two really cannot operate without each other. But remember, the thermal overload switch should be an independent switch that checks whether the motor temperature is exceeded. If it is, then it should engage to stop the motor, even if if you don't engage the push button. And at the same time, the push button, if engaged, should be able to stop the motor, even if the temperature of the motor has not been exceeded. But the way it is connected here, it's that we must consider both conditions. So that is where the problem is. So if I were to draw this ladder diagram, then rung number 2 would change, so that now you connect the stop push button and the overload switch, you connect them in series. I mean, you branch them out, not in series, you connect them in parallel. You branch them out, so you connect them in parallel, so that you have if the stop push button, or, so this, we should have this here, we should have it here. Now, please remember, again here, you can see that the stop push button is connected as a normally closed contact, and the overload switch is also connected as a normally closed contact. The idea here was simply to illustrate what happens within the software part. We are now not considering what is on the physical device side, okay? So the issue is not really on the device, the physical device side. The issue is how the virtual connections have been done, okay? That's what we are testing here. So this is simply testing, not really that we must have the stop push button and the overload switch connected as normally open contacts. This is just to illustrate that if you were to simulate this, you would notice that the problem is there would have to be a condition, that combines both the stop push button and the overload switch. So rung number 2 should be connected in parallel rather than in series. Go ahead, please. I have had that's a good question. I've had this question before because indeed sometimes it becomes very confusing, especially if you remember I had told you before that there's a way engineers look at things and then there's a way software developers look at things. Now the software developers don't know how we do the physical connections, but engineers know how we do the physical devices because engineers are the ones who also design and manufacture the physical devices. So what I think I'll do just so that to make sure that there's no confusion here. One is we must agree that we are engineers, okay? Because that's what we are actually studying to do, and so that's our career path, okay? So if we are engineers, then we have to think as engineers. So what I'm going to do is, so that we don't have any confusion regarding these connections, is we'll have to assume that we are engineers. So the state of the physical devices would really matter, especially because if you look at the way we have done the connection here, you can see that we've already connected, we've shown the physical, we've shown how the physical connections should be done. So unless otherwise stated, we'll always assume the condition of knowing the input field device positions and the output field device positions. So if I were to set this question, for example, I would indicate here that assume or not assume, I'll just say ignore, I'll just indicate ignore, I'll put a note if I were to set this, ignore the physical device connections, okay? Because I also understand that some of these questions, if you look at them, they might be very ambiguous, especially knowing that some of them or some of the ladder diagrams have been drawn by software developers or just, you know, people who are on the software aspect of ladder diagrams, and then or they're just PLC software guys, but then there are those that are also drawn by engineers who take cognizance of how the physical devices are connected as well. So for me, just to ensure that we do this in a proper manner, if I were to bring certain questions like this, then I have to be very specific. But the rule of thumb is think as an engineer, meaning always consider the connections of the physical devices. So if there's a unique case where you're not supposed to consider those cases, then I would probably have to specify to you that you need to ignore the physical device connections, because maybe it's not relevant to that point. It's just maybe to test if you can check a few issues that exist. So in this case, if it was not stated, then maybe one, you would state that we need to have these as normally open contacts. That's number one. Number two, we need to connect them in series, in parallel rather than in series. We need to branch them out. I don't like the word parallel and series because it confuses me with circuit theory and all that stuff. So in PLC, I said we need to branch them out. That meaning we connect them in the logical or position or fashion rather than the logical and fashion. Okay. So that's basically it. So always assume the physical device connections because we know them for start push button, stop push button, the thermal overload and stuff like that, unless otherwise stated. Okay, unless otherwise stated. I think that is the only way we'll get a proper setup. Now, please remember that if you go to the industry, you're going to encounter both professionals. You're going to encounter fellow engineers, and you're also going to encounter just software developers or just programmers. Just programmers. They know nothing about the physical world. All they're doing is in the virtual domain. So usually it's important to understand who you're speaking to so that when you're communicating, you don't have arguments as to what position should this contact be at. So you should just be able to know if I'm speaking to an engineer, then we know the state of the physical devices. But if you're just speaking to a PLC programmer who has no background in engineering, then of course we'll have to look at the virtual way of simulating these things. So we have to look at them in terms of just the virtual devices alone without the physical devices. So at least you know at this point that for you understand both scenarios. So all you have to do is figure out when to use or to invoke a certain scenario based on your skills and knowing who you are dealing with at any particular point. All right, so be that as it may, if I did ask this question, or if I didn't maybe give this caveat, then you would indicate that one, we just need to have this connected properly, the start push button and the stop push, or the thermal overload switch. We need to have the stop push button and the thermal overload switch connected as normally open contacts. And then they also need to be connected in the logical or fashion, not the logical and fashion. All right, good. Let us move on to the third one. Let's see. Now, I think maybe one of the problems with this, not just this question, one of the problems with this tutorial that I gave you, maybe I realized it later, is that the question itself, I needed to be very specific or more detailed, for that matter. I needed to be more detailed in instructing you on what to do, because you can see that here I only indicated that you need to identify the problems and modify them, okay, as they should. But maybe for each case I needed to have indicated, maybe case 1, consider physical devices. Case 2, ignore physical devices. Case 3, this is the condition. So maybe there are certain conditions that are not very clear, and so it makes it a little ambiguous in how to solve it. And you'll notice that even with the third question, I was trying to scan through the third question to try and see the solution, find the solution to it, and I realized that the solution really is based on the question. The question is not sufficient. Yes, that's the word I'm looking for. The question itself is not sufficient to give you a proper idea of where the problem is with ladder diagram number 3. Because if you look at ladder diagram number 3, there isn't any problem with it. It will work. So the reason why I say the question is not clear is because I understood that there is another way of connecting this. So there are 2 scenarios here, and that's why maybe allow me to share this with you, and maybe you can include it in your own way in your question, so that next time when you're revising, you understand it clearly. You see, in ladder number 3, ladder diagram number 3, it's a very simple diagram, and I didn't find any problem with it. I only figured that maybe there would be a problem if there was a condition that was given that was not followed. And that condition, I'll tell you in a short while after we have understood this ladder diagram. So let's understand this diagram, but let's make it clear, ladies and gentlemen. There is no problem whatsoever with this ladder diagram. It will work, okay? Let's see how it works. That's where the problem might be. How it works is the problem. If it works, it's not an issue. It's going to work. But how it works might be the problem. And it might be the problem if it was clearly stated in the question. But the question does not clearly state what the problem is. So let's see why I'm speaking like that. That the problem is not whether the ladder diagram works or not, but the problem might be in how it works. So you have a start button. So assume you've energized your start button. So definitely if I energize my start button, I expect a logic 1. Okay. The stop button is already passing a logic 1. Remember, it's connected as a normally closed contact. So it's already passing a logic 1. Okay. The overload switch, or maybe I should start. Okay. The overload switch is also already passing a logic 1. So that then passes the logic 1 to the enable output. When the enable output is given a logic 1, the input also gets a logic 1, so that even when you return the push button to 0, we still have a path to follow like that. Okay, that one, the latching, we already know that. I just want to figure out what happens to this ladder diagram. So rang 1, rang 2, rang 3. So in rang 1, let's have the enable output being given a logic 1, and therefore that is transferred as an input of rang 2. So rang 2 has gotten a logic 1 because it's the input. Rang 2 now has a logic 1, meaning it energizes the on delay timer. Because when the on delay timer has been energized, then it starts counting. The clock that exists in the timer starts counting to achieve the preset value. The preset value here is 3 seconds. Remember, I told you that these devices are usually set in seconds. So it means that this device will count in steps of 1. You see, the time base is 1.0, so it's counting in steps of 1. So the clock will need to click 3 times. If it was to count in sets of 0.5, to reach 3 seconds, the clock will have to take 6 times. I hope you now understand that. To achieve the preset value, the clock needs to know the time base. How many clicks do I have to make to achieve the 3 seconds? So here, because the time base is 1, it means the interval is 1, the clock will have to click 3 times for it to reach 3 seconds. So once it reaches 3 seconds, you already know that the done bit would be energized. So therefore, remember, I pressed the push button. Okay? That pressing of my push button provided a logic 1 on the enable based on the conditions, because those conditions are already met. You'll have a logic 1, and then that would energize the timer. The timer will have to count 3 seconds. Then there would be a done bit given a logic 1 there. And so if the done bit is given a logic 1, that logic is transferred to the motor. And so the motor starts. But remember, here, therefore, it means that I can press the button and release it. I don't have to hold on to the button. I can, because this is a latching circuit. So I can press the button and release it, and the motor will not stop because we latched the circuit. I can't explain that further. So the idea here is the way this ladder diagram is set to work, and it works, is that somebody presses the push button, and even if they release their hands, so that means they momentarily press the start push button. You can release your hands. Then the motor will have to have a 3-second delay before it starts. So the way this circuit works is that when you press the start push button, you have a 3-second delay before the motor starts. And the pressing of the push button is just momentarily, okay? It's only for a short duration of time. You press and you can release. And because it is latched, even if you release your hand from the push button, the motor would still run because you have a logic 1 here. There's a path here of OR, okay? So therefore, this circuit works, and the way it works is that somebody presses the start push button, and then 3 seconds later, the motor starts. So therefore, this is in a case where you'd want to press the button, but then you'd want the motor to wait for 3 seconds before it starts. I don't know of any applications that require you to start something and then there's a delay before it starts, unless there was something that you wanted to happen in between before it starts. Because by the time you're going to press the push button, it means you want the motor to start, okay? So unless there's another unique application where you want a delay between the time you press the push button and the time the motor starts running. So that's probably where I got a hint that there might be a problem, because typically, and that's why I told you, I don't want you to have abstract thinking. I need you to think as though you are actually working out in the real world. So typically, why would anyone want to go and press a start button to start a motor, but they don't want the motor to start immediately? Okay, unless there's a unique position where you want to start the motor, but you want to move far away before the motor starts because of conditions of either the motor is so loud and it's maybe the conditions there can be dusty and maybe you don't want to put yourself at risk. So you press the button, you have a delay of some time to walk away to safety before the motor begins. So maybe the condition where the motor is, but usually again, you can wire the start button to be closer to you and the motor is very far away from you. The start button shouldn't be really just in close proximity to the motor itself. So if there were such conditions, then I would have a switch in a safety room and the motor is in its own, production hall. So I'm not in any way endangered. So that's where I figured that there might be an issue, where the question really here wasn't asking if the ladder diagram has an issue, but if you can identify how the ladder diagram works and see where there could be an issue. And for me, the issue here would be there wouldn't be a need to press the start button and then you have a delay of 3 seconds before the motor starts. So the ladder diagram works well, but how it works is where there might be a problem. That this one works in such a way that I press the start push button, but the motor doesn't start until 3 seconds later. So now, if you want, because then the question would be, how should it work then? What was the alternative way that you are looking for? And what I think the question wanted to ask, that's why I told you the question might have been ambiguous, or it might have lacked a certain piece of information that is critical. How it might have worked is that maybe the idea is you're supposed to press the start button, but you don't release your hands until 3 seconds elapse. So that means I need to press that green button for at least 3 seconds before the motor starts, because that I have seen in the industry quite a lot, that for the start button, you need to engage it. And just like in your phone, you see, if I wanted to switch on or switch off my phone, you've noticed that just pressing the button once, the on off button for your phone, just pressing it once really doesn't start or switch it off, doesn't switch it on or switch it off. You must long press. We call it long press, or you hold on to that button. So that is an application that is more common than what we have here, where so it's like saying, if I press my phone, then I just need to press it momentarily, then 3 seconds later the phone starts. Really, that's not an application that anyone wants, because I want to press my phone and I see it start working immediately. So maybe the only mechanism is I need to long press the start button. So I need to hold my hand on the button for at least 3 seconds for me to see the screen lighting up and my phone starting. Okay, so that is a safety mechanism, because otherwise, if it's just pressing it short time and then it starts, it means every time you touch that button, your phone is switching on or switching off, switching on or switching off. But if you long press it, it's a way of ensuring that you are intentional about switching it on. So you are actually long pressing to show that I know what I am doing. I want it on. So that's what I gathered would probably be the real the proper ladder diagram. That we need to redraw this ladder diagram so that you have to hold your hand on the push button for at least 3 seconds before the motor starts. But in this case, you can only press it momentarily, then there is a delay of 3 seconds, then the motor starts. But that's not what we want. We want to press the start button, hold that press for 3 seconds, then the motor starts, because then it shows your intention of starting the motor. It's a security mechanism for ensuring that, because somebody would by mistake nudge or just touch the button, and then the motor starts when probably they never intended. But when you long press, when you hold the press for 3 seconds, it shows that your intention is really to start the motor. So for me, when I was considering this thing last night, I figured that probably is the is the logical way of drawing this ladder diagram. So we want to transition this ladder diagram from just being pressed momentarily and then the motor starts 3 seconds later to a point where I need to press the push button, the start push button, for at least 3 seconds, and then the motor starts. So how would you achieve that? It's not a very difficult thing. It's a very simple thing. You see, if you look at this ladder diagram, the delay, where you put the timer is key. Here, the delay is on the enable, on the energy of the timer. So, like, you press the button, but when you press the start push button, it only energizes the enable input or output, whichever it is. And then that then leads you to a timer. So you are delaying the time that the motor starts, but we want to delay the time that you press the button for. So you press the button for a longer period of time. So then that becomes a very easy thing. We can do it in probably even 2 ranks. Do I have space here to draw it? So what that means, therefore, is that, yeah, I can use the same, let me use the same diagram to change so that you see it. I don't have space to draw. So therefore, what we can do is change this enable, we remove this, and we make this the motor. Okay? So that the push button is not engaging the enable or the timer. Here, the push button is engaging the timer, then the timer is delaying the time for the motor to start. But we want the push button to be delayed. It is the action of pressing the push button that we want delayed, not the action of starting the motor. The motor should start immediately, but at least the push button should be pressed for at least 3 seconds. So after those 3 seconds, the motor should start. But in this case, the start button engages the timer. The timer delays the time that the motor takes to start. So here, if I change this to a motor, okay, and so because it's a latching circuit, this also changes to a motor. So this is still the motor. So I can change this to a motor, okay, like that. So we remove the enable, okay. Let's just see. Then we remove this push button, because remember our idea here is we want to delay the push button. We don't want to delay the motor from starting. We want to delay the length of the push button. When I say the length, is the duration in which you press the push button. That's what we want to delay. So meaning the motor should start based on the delay of the push button. So this enable here, we can change it to the push button. Okay? So because now, think about it. So if I change it to the push button, then the done bit, so let me just make this the done bit. This becomes the done bit for the timer. So let me just write timer done bit. So this is your timer done bit. Okay? Then now we don't even need this rung. We don't need this. This is unnecessary now, because the motor is already up there. So this is unnecessary. Sorry, it might not look too neat, but it's just because I don't have space to draw it. And by the way, I'm done. So look at this. Let's see if this works. So we've removed this. Let's see this now. So here it means that the motor is energized based on the timer done bit, the push button, and the overload switch. Okay? But the timer done bit is conditioned by the start button. So it means, therefore, let me tell you why this now I think works. It means at first, before I press the button, let's see, before I press the button, what we have, the done bit is 0. Yeah, because the done bit only comes after the timer has counted. So before the timer counts, the done bit is at 0. So if the done bit is 0, the push button, please remember, is already allowing logic to pass through. The overload switch is also allowing logic to pass through. Okay? So therefore, but because we have 0 end, we know that an end function, if you have any one of the inputs as a 0, then the output is a 0. So we expect this to be 0, and so this is 0. I hope that is very, very clear. Let me repeat that. We are saying before we do anything to this motor, the done bit of the timer is at 0. And so this point is 0. The push button is already allowing logic to pass through. Remember, the push button requires that when it's engaged, it breaks the logic so that the motor stops. The same thing with the overload. So as it is, it's allowing logic to pass through. So it's at logic 1, logic 1. But because the on delay is at logic 0, this is at logic 0. And so the input mirrors the output. So that is also just at logic 0. So notice rang 1, the output is a logic 0. Okay? Now, let's come to rang 2. Rang 2, before you press the push button, it's at logic 0. But now, let's see what happens if you press, because now it means the motor in this case, because notice it's 0, so the motor is not running in this case. It's not running. But now let's see, if I press the button, so there's a start button there. Okay? So if you engage the start button here, then now I close the contact. So I get a logic 1 here. So notice it's the start button that I have engaged. But because I've engaged the start button, notice that it is connected to a timer. So that engagement transfers that logic to the timer, okay? Because I've engaged the start button, it transfers the logic to the timer. But the timer will not activate this until 3 seconds later. So it is after 3 seconds that we have a logic 1. So notice I'm pressing the button, but the output will only come out after 3 seconds. I'm pressing the start button, but the output, meaning the done bit, will only be a logic 1 after 3 seconds. So therefore, it means I'll have to press that button for at least 3 seconds. Then the done bit will be a logic 1, and then that will change this now to a logic 1. And so we have a 1, 1, and 1. This definitely will go to a logic 1. The motor will start, and then it will latch. Okay? So here, the difference is we are delaying the action of pressing the start button. Because now, initially, we were delaying the action of starting the motor. The start button had been pressed, but it was going to an enable output, which is to energize the timer. But now, we are not delaying the motor. We are delaying the start. So the action of pressing the start button is going to be delayed by 3 seconds. Typically, we know that whenever I press the start button, then that logic is transferred immediately. But notice that now the start button is connected to a timer, meaning the output that is achieved by pressing the start button is going to be delayed by 3 seconds. So therefore, it means that my hands will have to be on that start button for 3 seconds at least for the output to be a logic 1. And if it's a logic 1, then now the motor will start based on rang number 1. But before that, there's nothing that will happen. So the essence here is we are delaying the action of starting the button. So the pressing of the button has to be a delayed period of 3 seconds, not the action of starting the motor, because you can see that as soon as the done bit is 1, as soon as the done bit is 1, the motor will start immediately. So what delayed was me button, but not the previous one was delaying the time that the motor takes to start after I had pressed the button. But here, before I press the button, there's already a delay of 3 seconds. So me pressing the button will take 3 seconds before the motor is engaged. So that is what I think was the intention of the ladder diagram. So if it was asking that, because the question is identify the problem or problems with each of these PLC programs and modify them to work as they should. So this is how it should work. This is how it should work. That typically we usually delay the process of the start. So it's the start button that I must hold for 3 seconds before the phone starts. Note that I press the button momentarily and then 3 seconds later, that's when the phone starts. Because then people would start saying, then my phone is slow, I press it and it takes some time before it even starts booting. So to boot my phone, I have to actually long press the start button, okay? And that is exactly what it is with this motor. If there are any questions, the first hour is gone. Let's hear them. Let's hear them. But my apologies, because I said, if you're not keen, because it took me time to also digest this ladder diagram. I was looking for a problem, I didn't see it. But then I figured then the problem is not really in how the ladder diagram is drawn per se, it's in how the ladder diagram should work, not really on the connect. The connections will still make it work, but it is not working in the right way that it should have worked. The first one was delaying the time between the push button being pressed and the motor running. But this one is now delaying the action of pressing the push button. But once that delay has been achieved, then the motor starts working instantly. Kama kuna swali, let me check again the wall. I see, no, I don't have any. Okay, I already see. Yes, let's hear from Davis. Davis, ask your question.
Hello, do you get me?
Yes, go ahead.
Okay, my concern is, you remember when we started our lectures on timers, we were keen to say that the connection of the timer, the enable bit and the done bit, only one should be connected on the output rail. And the reason as to why we were saying so was because we never wanted to have timer reset issues, in the sense that when you have the done bit connected to the output, then it can trigger a reset of the timer's accumulated value before the timer reaches its preset value. So I'm actually concerned, because I'm thinking having the enabled bit and the done bit connected to the output rail might also be a problem for run 2, because that will mean that the timer will have timer reset issues. It might reset even when the preset value has not already been reached. I don't know if you can say something about that.
Yeah, yes, Davis. That's a very good observation, actually, and I'm really glad that you guys can be able to figure out stuff like that maybe are not very straightforward. But if your point is exactly true, and I agree with you. However, the difference, the biggest difference is the done bit is the one that's usually connected to the output device, not the enable bit. Yes, I agree with you that the enable bit essentially should not be on the output rail. But the comfort is that it is the done bit that's usually connected to the physical device. So if I were to connect this to the motor, it is the done bit that's actually actuating the action of starting the motor, not the enable bit. But truth be told, I have also looked at this before when I was studying timers and stuff like that. And I was like, the enable bit is always connected on the output rail as well. But if you think about it, what function does it usually perform there? I usually see none, because the action of the timer, usually we are always interested in reaching the preset time. Then we activate the done bit. Then it's that done bit that we use to actuate the next device or the physical device. So I quite agree with you. Sometimes There may be other applications where it's the enable bit, but I've never actually seen where the enable bit is the one that's actually taken to actuate the output. It's usually the done bit. So I agree with you that this can also cause issues with the, prematurely presetting the timer and stuff like that. But as it is, let's stay on the fact that we understand that on the timer on delay, we are basically interested on its output, which is the done bit, not the enable bit, because then the reason why this enable bit might be here is because sometimes you might need to cascade the timers, or maybe reciprocate timers. And so then the way you connect them sequentially would require an enable bit on that side, but we don't necessarily use it as an output. Yeah, it's the done bit that's considered the output of the timer, not the enable bit. Okay, so I hope that is clear, that the output of our timer is usually the done bit, not the enable bit. But I know that the way it's connected, it's in such a way that it's usually in the output. And so somebody would be like, it means that we can take the enable bit and use it upstream. But in real sense, we are only interested in the done bit because it's the done bit that's usually connected to the physical devices. But the enable bit might be used whenever we are connecting, timers sequentially or cascading or reciprocating them. Okay. Sawa Davis. Before, yes, Ogola, you could ask, but before you do, I see Sherry is asking, will the rank order remain the same? Yes, Sherry, yes, the rank order remains the same. This remains rank 1, this remains rank 2. Think about it. The sequence of operation is such that what happens if you change the rank order? What happens if I change the rank order? I don't know. It does sometimes, because this is a revision. Maybe let me hear from you guys. Would you rather have it rank 2 to be rank 1, or would you just have them to stay the same? Does it change anything? Because we are revising. So let me hear you guys. Let me hear your thoughts. What do you think? Anybody just comment. What do you think on the rank order? Do we leave them as they are? Because they're now just 2. Or do we interchange them? So that, because we are used to the start push button being on the first rung anyway. Or should we just leave them as they are? I did a comment here. It's important. Okay, so Ismail feels that we need to interchange so that rank 2 now becomes rank 1, and then rank 1 becomes rank 2. Okay. Any other opinion? We are talking about the rank order. Ogola, will just give you a minute. I mean, just give us a minute and then you will comment. We just need to understand, is the order of the ranks important? Usually the order of the ranks actually is important. In this case, do we interchange them or we leave them as is?
For me, I think it will work either way. But if we had other contacts below rank 2, then we would have to interchange so that rank 2 becomes rank 1 and rank 1.
Okay, thank you, Emmanuel. Any other thoughts? Last one. Any other thoughts? I see Kipruto is also agreeing that this should work. Yes, Ochor, just go ahead.
Yeah, I'd also say it should still work, because from the scan cycle, the first step is to read and check all inputs. So it doesn't matter where it will be.
Brilliant. Thank you very much. Actually, that's what I was looking for. Sometimes I was waiting for the word scan cycle. And we know that our scan cycle is usually read, execute, and then update. So usually read is the first step. So even if we have it in this order or we interchange them, then it's still going to read and execute each of these components individually and only update the status of each of the contacts after reaching the last rung. So the order of the rung here isn't really going to change much for the controller or the processor, the PLC processor. So because the scan cycle dictates that you still have to read through the state of each of the components, then execute them based on the Boolean expression for each one of them. And then once you have reached the last rung, then now you update the status of each contact. So it means, therefore, that it doesn't really matter the ordering of the rungs in this case. It wasn't really going to change much. But somebody mentioned something that's also critical. If we had other rungs, rung 3, 4, 5, then sometimes the order might be important because one rung was probably going to lead into another rung. But the way that our circuit works, our ladder diagram works in this case, between rung 1 and rung 2, there isn't really an important issue in the order in which we connect the rungs, because ultimately, we are still going to read through all the instructions, execute them, and then update the status after all the rungs have been exhausted. Okay, so it's not really having any effect. So Charlo, you are right. Tony, you are right. And so I hope, Sherry, you have been answered. Thank you guys, Ochor and Emmanuel, for your contributions as well. Okay, now somebody wanted to say something. I think it's Derek. So go ahead, please. Before we move on, time is not on our side.
Yeah, mine was just about not necessarily this, but just dealing with the timers as well, where maybe you have the timer controlling a counter. So like I realized that when you just connect the timer directly with the counter, you will all obviously just need that pulsating signal to reset and set the timer as well to maintain that counting. So because already we've completed with this, that's just what I wanted to ask you. Just for that, maybe I can present a simulation, just maybe for pure understanding of what I'm saying basically. Then
you want to present now?
Yeah, just maybe like 2 minutes.
Okay, sawa. Go ahead. So I'll stop sharing, so that you're able to let me just stop sharing. Sorry, I forgot that. Okay, so let me stop sharing so that you can share.
Yeah, I hope you can see it.
Yeah.
So like maybe just you have the timer controlling the counter. So maybe when you put it on, just realize, yeah, it is on, yeah. Just realize maybe to just count within the preset time. So that you just have just a particular one count. So during that time, you just realize that when you set the timer on, if you just have one count, you obviously will have to have that reset and preset system to make the counter continuously count within the preset value of the counter. Yeah. So because like the previous examples we did in class were just modeled in this format, but now when you go to the simulator, you have to maybe again have to modify the PLC ladder diagram as well. Yeah. So with this, I realized that I can introduce the reset and preset model of the timer, so that we'll continuously get that pulsating or pulsating signal to continuously set the timer for the counter to continuously count within the preset value of the counter. Yeah. So I don't know what you have to say about that.
There's nothing more to say, Eric. Actually, this is very interesting that, and it's true. You see, that is why sometimes I get worried that when we do things just in class and we use some of the abstract examples that we see in class, you might not really get the 100% picture, because the ultimate thing is when you use a simulator, you will actually see how some of these devices really work, and then some of the latching or set reset mechanisms, you will see that they don't exactly work exactly as we say in class, but they could work slightly differently. Like in the case you're explaining, it's very correct that for you to sort of like have a continuous count, then you need to have a mechanism of continuously resetting, and therefore you might have to change your connections. And the thing is, you might be shocked that that only works with this PLC. I don't know which PLC this is. Which PLC this is? What's the manufacturer for this PLC?
It's just an online based, yeah.
Oh, it's online based.
Yeah.
Now, yeah. So my point was that you might find that the operations vary based on the kind of PLC you use. Okay, it's online based, but it must be based on a certain PLC manufacturer. So maybe you can check that later. So usually, some of these things, yes, what we give in class is a general structure of how the PLC works, but you'll realize that each of the PLCs have they have an underlying working principle because they have their own data sheets, but the principle of operation is the same, but there are certain differences in how they actually work. And you'll only know that when you actually simulate with that PLC. So if I simulate this exact same example with Siemens and with Rockwell or even with Omron, you might see that there might be slight variations in the performance, because the timers have slight variations, the counters have slight variations from manufacturer to manufacturer. The variations are not so wide as to change the entire thing, but they're only small, but requires that you know about them. That's why they are accompanied by data sheets, so that you don't assume that all the PLCs will work exactly the same. The principle of operation will be the same, but there might be slight variations in how they work. So again, I appreciate this because it shows that you guys can now relate what actually works in real life with what we discuss in class. Some of the principles might not really come out when we are talking about them in class, but when you actually do the simulations, you can see the typical variations that exist. It would be very difficult for me to point out this case in a class scenario unless it is simulated like now, unless we're in a simulated environment like it is now. That's when we can probably understand some of these concepts. That's why even when I gave you the tutorial, I was really hopeful that you will try, and I'm glad most of you have done that. You will try and simulate them on your on any platform, but at least so that you see the working principle on a simulator rather than just talking abstract information based off of theory. So this is okay, but I'll be honest with you. If you try another PLC, it might not work exactly as this. They may work the same way, but some PLCs might have some level of difference, because there are certain features that are added to timers and counters by some manufacturers that are not added by others. So again, it depends on the PLC you're working with. And so the idea, and that's why you are the engineer, you need to figure out which one works and does it provide the output that you expect. If it doesn't, then what adjustments do you need to make so that it works? So sometimes the problem is not really with you or your design or your ladder diagram for that matter, but it's with the PLC that you're using. And so it's usually also a very good consideration to check, what PLC do I use? What's their data sheet? What are some of their instruction sets? And then how do we then achieve my objective using this PLC? So thank you so much, Eric, for this illustration. Really is an eye opener, even for me, because I can't simulate all environments myself. I'm also just tunneled, or I'm narrow-minded in exactly my objective. So some of this I also learned from you guys. So thank you for your comments.
Let me take a minute to modify so that at least we can have a...
All right, go ahead, please. So when you're modifying, you mean you're now removing the counter?
No, not really removing the counter, but just to make sure that I can reset and reset the...
You want to reset continuously?
Yeah.
Okay. I hope at this stage, every one of you is able to at least simulate something in any PLC, even the one that exists online. If you at this stage are still not able to do stuff like this, then there might be an issue, or maybe you just not planning to deal with PLCs. But in the world of automation today, I think there's no way you'll escape some of these things, especially as an engineer who is going to practice engineering, especially in control systems. So it's important that you really also try and do this. We can't test this in an exam, but this is what you'll encounter in the industry. So it's important that you code your skills around this area as well. So I see.
Excuse me, sir.
Yes.
Yeah, as Eric connects, I had a kind of question. How will now AI be incorporated in PLCs now with machine learning and everything?
That's an interesting question. So you probably want to see what's the convergence of AI and PLCs. I wanted to answer the question with another question, but then I'm thinking, would it be right? We know what AI is all about. Of course, it's trending, but we know that AI is basically based off of training computer systems to be able to mimic human behavior, and it is based off training. So that means data is important. So the more data we provide it with, and then we give it the algorithms for learning this data, because data can be jargon, it could be junk, garbage in, garbage out. So we must be able to figure out what are the appropriate portions of the data that it must then use or we use to train it. And then once they have learned the several techniques, then they're able to now make independent decisions to help solve some of the problems that we have. But you will notice that aside from that, in control systems, the PLCs really they are still computer systems as well, but they're not based on data. There's no training involved. What we have to do ourselves is there's still physical wiring involved, okay? Because as much as we are drawing ladder diagrams, we still have to connect them to some physical devices. So there's physical wiring involved. There's ladder diagram involved. So maybe for me, the convergence would be if we could train an AI to be able to help us come up with a ladder diagram. The essence is to make our work easy, to minimize the error, and to maybe perform more efficiently. So the time it takes me to come up with a ladder diagram, and based on compared to what an AI could do, of course, that's way different. So maybe AI is a tool that we can use when, as control engineers, we can use AI as a tool to help us develop ladder diagrams more easily or more quickly, and they are less error prone. So troubleshooting is minimized and stuff like that. So I think for me, that's where the convergence could be, but not really as in one replacing the other. I don't see the connection. I don't see the connection where we have to to replace, PLCs with AI. I don't see it at all, especially because we even have to involve some physical connections. Unless there's somebody else, because this is just, we're sharing our comments. So unless somebody has something to say. But what I know is that as we have to, AI is a tool actually, but PLC is a system. PLC is a system. So we can just use the AI tools or the AI capabilities so that we put them in our PLC systems to sort of enhance the operation of our systems based on efficiency, troubleshooting issues and stuff like that. So AI is a tool that can be used in industrial automation, but I don't think it's something that can help us eliminate or replace control systems. So, is it Ismail who asked the question?
Yes, it's okay. I was kind of wondering if it can be incorporated into PLCs, having the AI kind of doing some prediction and optimizing some processes and
correct. Prediction, I am not too sure, because look at it this way. Our control systems are not really based off of predictions. They're based off inputs and outputs, okay? AI predictions would be things like weather patterns, so those would need data. It would be stock markets, those would need data so that you predict. But for control systems, you have an input, you have your plant system, and then you have the output. So, but you're right, they can be used to help optimize your industrial process. So you can use machine learning or even deep learning or whatever it is, but you have to use either of those as a tool to help you optimize your systems, maybe to reach a conclusion quicker. Because if you think about it, control systems like we are talking about, even in PLCs, there are delays involved. But now if you use AI, there's probably a way in which we can eliminate some of those delays when we are using AI. And so it helps you sort of optimize your system to mimic a real time. Everything we do today, we expect that the output is going to be given after a few milliseconds, or seconds or hours, whatever. But we expect a delay between the point we give in an input and the point we get at an output. So we can't really mimic real-time events. But with AI, it's possible that we can optimize our systems or processes to sort of have a real-time effect because of the capabilities of machine learning or deep learning to either work more efficiently, or even in your case be able to predict, so we can get the outputs much faster. So you're right. There is a way we can converge AI or we use AI and deep learning tools to optimize our systems. Think of AI as a tool, not really as a system in itself. It's a tool. It's like MATLAB. It's like MATLAB. It doesn't really replace your system, but it can enhance the operation of your system. But you can replace it as well. You can you can replace AI with a different tool. Okay. Yeah. So it's a tool that really can assist. And that's good. I think I'm going to think of a project for maybe a student next year around that area. All right. Where are you so far, Eric? You're done?
I'm already done. So I just wanted to maybe activate the simulate, and also like I've just reduced the interval between the counts. That's the counter count.
So you've introduced, because I'm seeing in your rank 1, I see a pulse. Oh, rank 2. Oh, okay. So it's an output. Okay. 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 So you want it to continuously generate the pulse?
Yeah, absolutely.
Oh, okay.
So when I activate, you can see like it provides that continuous.
Yeah. So yeah, so it repeats. Okay. Okay. Oh, this is brilliant. Yeah.
It's 9:30.
Yeah. Yeah, we know it's 9:30. All right. I think I can see that's good. That's good. Oh, this is nice. I'm learning a lot of things from you guys. Maybe I should have had more virtual environments where we do these simulations, and I also get to see a few things. Yeah. So once the preset value is reached, then we regenerate the pulse afresh.
Yeah.
Okay. And that means that now we can proceed for longer.
Yeah, sure.
Okay. I hope the other guys can understand what we are talking about. If they don't, then maybe they can side chat you so that we are able to continue. Now, guys, I told you I have only 30 minutes remaining, and I told you I am ending my classes with you guys on Wednesday so that I give you enough time to study on your own, so maybe if we don't, then maybe I'll have to extend it to next week, Monday. But I wanted to end the class this week. So let me quickly rush through the last one. Thank you, Eric, for that illustration. Let me take time to go through the next one quickly and see. I might not complete it. The problem is I don't have solutions to these questions. I was actually just trying to also look at them last night. So let me see. Let me quickly share my screen again so that we go back to this. So I hope this is clear. I told you we don't have a problem with this ladder diagram in its operation, but maybe the way it operates is where the problem is. The how is what the problem is. And I hope now it's very clear. So question 2 is also very important because it's also just testing our questions on ladder diagram. Perhaps I see question. Hey, question 5. Okay, we'll see. We'll see where we end. We'll probably just do others on Wednesday. But at least let me try and see if we can finish question 2, so that maybe on Wednesday we can, because Wednesday is 1 hour. But if you give me 2 hours, then we can complete the rest and then we conclude. So let's quickly look at question 2 because that's also very important. And I think let me see. Okay. Let's see. I'm trying to see. Okay. So the question here again is simply from an engineer's perspective. Now it's written an engineer, so it simply should change your thoughts that you're actually thinking of an engineer, and so you're thinking of the physical devices as well, not just the virtual devices. So we have to write a PLC program as an engineer to control a water pump that's driven by an electric motor. Now the pump will be manually started, so there's a physical push button and stopped. So there's a physical stop push button, a physical start push button, and shut down automatically by one of several permissive switches. So there are a lot of switches here that are involved for starting the motor, for stopping the motor, and also for shutting it down for whatever reason. We'll look at those. The operating statuses of these switches are listed. So I think you have gone through this as well, but the idea is to be very specific on what has been mentioned, and you stick to it, because that's where you might have issues. So if I can complete this quickly, the start button is connected. So there's a switch which is physical. It's in the normally open position. So this one we are used to because we've dealt with the start button as many times as we've looked at ladder diagrams, and they're always connected in the normally open position. The stop push button is indicated here as normally closed. Again, the operation of this stop push button we have done severally, so I cannot look at it further. Then there's the low water level. So there's a switch that's called low water level. That switch it's indicated here as it's always normally closed. But again, it's specified that when it is closed, it means that the level of water is low. But when it's open, when the switch is open, then the level of water is adequate. Think about it. Motors need to cool. So what cools our motors is typically water. because you can recycle it and it's not expensive. So even an engine. So we use water for cooling. Some I know use oil, but that's expensive. Water is not. So we use water for cooling. So here, if the water level is low, the motor should be shut down. That needs to be clear. That's why we have these conditions. And when the water level is adequate, then the motor should just be running. So therefore, you can see that the condition provided here is that the switch in its normal position is normally closed, meaning when you press the switch, you open it, because the condition is it's in the normally closed position. So if you engage it, then it means you're opening, you're breaking the circuit. When it is open, that's a condition for adequate water level. But when it is closed, that's a condition for low water level. We'll come back to that. Then there's the low oil pressure. That's connected to a normally open contact. Now, meaning if I engage this switch, then I close it. But it is supposed to be closed when the pressure level is adequate. When the pressure level is low, then it's supposed to open, because again, if you have low oil pressure, you should not operate your equipment. So in this case, the switch is normally open. So therefore, that means that if I engage the switch, then I'm closing it. And it's supposed to be closed when the pressure level is adequate. And it's supposed to stay open when the pressure level is low. Okay? We'll come back to that again. Then there's vibration as well, another protection for the motor. So we don't need very high vibration. So the high vibration, the contact is already wired as a normally closed contact. Now, it says here that when you leave the contact as is, then we are assuming that the high vibration is still, there's no vibration. But when it is open, meaning if I engage the high vibration contact, meaning if I energize it, that means I break the contact. I'm supposed to do that, or it's supposed to break the contact when there's high vibration or when the motor is vibrating, because vibrations also have issues. The loose parts parts will come loose, and then it might bring issues to your motor. Then there's also the water leak, which is in the normally open position. So it's open when dry and closed when wet. So if there's a leakage, this detector, water leak detector, is supposed to be closed. Okay, if there's a water leak, then it's supposed to be closed. So now the engineer is drawing a ladder diagram, but they're saying that the first ladder diagram he has drawn has some serious error. So we need to identify and correct that error. So again, I can see here that the big issue is on how we connect our ladder diagram based on the condition of the physical device. Based on the condition of the physical device. Start push button. Let me make them here. Actually, drawing them helps a lot. So you have a start push button, which is in the normally open position. You have a stop push button, which is in the closed position. Then there is the low water level, that is closed position. The low water level, low water, that is in the closed position. Low oil pressure is in the open position. So you have the low, so this is called low oil pressure. So low oil, that is in the open position. Vibration, high vibration is in the normally closed position. So high vibration is in the normally closed position. And lastly, the water leak is in the normally open position. So water leak is in the normally open position. So those are the positions of this, okay? Some are closed, some are open. But now we need to check them based on the connection of the ladder diagram and identify which one is not connected properly. Now, we know very well the start button is connected properly because it's normally open. Here it is normally open. Now, let's look at how the diagram works. the diagram works in such a way that, again, it is latched. That's fine. You press the start button, you have the stop button, then there's a shutdown. Now, this is the condition where you're shutting down the motor based on the conditions that I've given here. And so this shutdown is put here as a normally closed contact, meaning for us to achieve a shutdown, remember this is a NOT gate. This is an equivalent, it's a NOT function. Let me not say a gate, a NOT function. So meaning if I give it a logic 0, the motor should be running. But if I give it a logic 1, the motor should stop. So because it is a shutdown, the only way to shut it down is if this is logic 1. Because if the shutdown output is logic 1, then despite the condition of the start stop button, this is going to be logic 0, and so the motor will stop. So shutdown is achieved by having a logic 1 here, because the shutdown is negated here as a logic to logic 0, and therefore the motor receives a logic 0, and therefore it shuts down. Okay. The conditions for the shutdown are provided here. So I don't think there's an issue with rang 1. The issue is in the conditions of the shutdown. That's what we need to look at. Is the water level connected properly? Is the oil pressure connected properly? The vibration high contact connected, and the leakage, are they connected properly? Let's see if they're connected properly. Meaning, let's see that if we combine the condition of the physical device, if you combine the condition of the physical device with the way the virtual device is connected, then it would lead to a logic 1, because that the shutdown conditions must be met properly. If they're not connected properly, then the shutdown will not be engaged properly, because whatever has been connected in rang 1 is typical latching circuit. So there's nothing different or nothing weird there. The problem is because the stop button you see is connected properly. It's a normally open contact, because here it is a normally closed contact. So we have talked about this. So the start and the stop should not be a problem. Those ones are connected properly. So we have an issue here with rang number 2. That's where we need to check. And remember, either of these conditions, that's why they're connected in a logical OR fashion, so that either of the conditions, if not met, then the shutdown is engaged. Okay? And the shutdown we know is when the shutdown output is a logic 1, so that the output in rang 1 should be logic 0. So let's start with the water level. So the water level, we were told low water level is in the normally closed position in the physical device. And they've indicated it here that it's supposed to be closed when the level is low and open when the level is adequate. It's supposed to be low. So the best way to solve this is to look at, does it meet the condition for the shutdown? Because these are just conditions for shutdown. So the way they're connected right now, do they meet a proper condition for shutdown? So let's see. So for the low water level, it's supposed to be closed when the level is low. It's supposed to be closed when the level is low. So notice when the low water level here, when it is low, it's giving already a logic 1. Because it's a normally closed contact. So it's already giving a logic 1. That is transferred to the virtual device. And therefore, that rhymes or that matches the condition for shutdown. So the water level is connected properly. In other words, what I'm saying is if this one was connected, let's say this one was connected as a normally closed contact, just saying, then the low water level, the physical device, is already passing logic. It's already a logic high. So the virtual device, if it's a NOT function, it will give me a logic 0. Because if it receives that logic 1, it will give me a logic 0. And logic 0 does not match a condition for a shutdown. So that is a confirmation that this one should be connected as is in the normally open position. Good. Let's move on to the next one. The next one is low oil pressure. The low oil pressure is in the normally open position. You can see it's in the normally open position, meaning as is, it is giving you a logic 0. The condition here is that it should be open when the pressure is low. We know that the condition for the shutdown is when the pressure is low, we need to shut down the motor. And when the condition is adequate, the motor can run. So this is very important. We need to shut down the motor when the pressure is low. And this thing is already connected in the normally open position. So we have a logic 0 here. This is logic 0 already. This is logic 0 already. And because we are dealing with low oil pressure, if you transfer a low oil pressure to a not function here, then you'll get a logic 1, which again matches what we have there. So I think the oil pressure is also connected properly because here it is in a normally open position. Low oil pressure is in the normally open position. So the virtual device should be in the normally closed position. So that, remember, it is indicated here, open when the pressure is low. So if the pressure is low, it should be open. Like in this case, it is already open, meaning the pressure is low, and therefore we need to engage a shutdown. So we have the logic 0 from the physical device being negated in the virtual device, and therefore meeting the shutdown condition. So I think that one is connected properly. Let's move on to the next one, which is the, which one is it now? High vibration. It's normally closed, but it's supposed to close when still and open when vibrating, meaning the switch should be open when we have a vibration. The switch should be open when we have a vibration. So as it is in the normally closed position. It's in the normally closed position, and indeed it's indicated here that closed when the pressure is adequate. So if it's closed, then it means that the pressure is adequate. But we need it to open when the pressure, not pressure, sorry. We are talking about high vibration. It's supposed to be open when vibrating. I was reading the wrong thing. It's supposed to be open when vibrating. So vibration high is our virtual contact. We have a high vibration contact already in the normally closed position as a physical device. So therefore, what that means, the condition here, we are supposed to have it open when we have vibration. It's supposed to be open, meaning logic 0 when vibrating. So let's say that the system is vibrating. There is high vibration. We are supposed to have this as open. We're supposed to have the high vibration as open, meaning if the system is vibrating, this switch should be open. But you can see that the switch is closed. So therefore, it means that we must connect this properly, because for us to engage a shutdown, we need vibration. For us to have a vibration, this switch at the physical device should be open, should be a logic 0. Okay, but it is already connected, or it comes connected as a logic 1. So therefore, it means that the only way to engage a proper shutdown, we need to have this as normally closed, so that it comes as a normally open. When that is negated here, it's a logic 0. And because we are told a logic 0 is what engages. Remember, they say open when vibrating. So what engages a shutdown is the open position of the switch. So therefore, we negate it because it comes as a logic 1. It comes as a normally closed contact. We negate it so that we are able to open it for high vibration, so that then we engage the shutdown. Now, and then the leak, water leak is normally open when dry and closed when wet. So therefore, it means that the water leakage, if there's a water leakage, we are supposed to have the device closed. I have forgotten the condition. Yeah, the water leak here was, this is already in the normally open position. This is the normally open position. So we are told that when there's a water leak, it's supposed to be closed. Yes. So if there's a water leak, we close this contact. And so if the water leak happens, we close the physical contact, and then this guy receives the logic, and then we have a shutdown. So basically here, the problem is this is the one that didn't work properly. Now I've made a mess here. Let me rub off everything and we focus on where the problem is. So I think clearly the problem is on our guy here, on this guy. This guy should be in the normally closed position, because the condition for vibration is it should be open when vibrating. It should be open when vibrating, but it is already coming. The switch is coming as closed already. The switch is coming as closed, meaning the switch is already passing a logic 1. So for us to have it pass, when it is vibrating, we disengage the switch. When we are vibrating, we disengage the switch so that we give it a logic 0. Okay, and so it therefore means that this needs to be a normally closed contact. Yo, my time is running down. Let me see where the problem is with the second one. The second attempt is below, but it also contains a serious error. Identify it. So notice now, in the second attempt, I see start button, stop button. Shutdown is now given as an normally open contact. So the engineers decided to use a normally open contact for the shutdown. So that means the shutdown condition should be logic 0 now. Yeah. Because we remember, shutting down meaning usually just means we give the motor a logic 0. We give the motor a logic 0. And so because he has decided to use a shutdown, it's his prerogative or her prerogative, whoever the engineer is. So it means to engage a shutdown, we need a logic 0 output. So if we want a logic 0 here, then we need the opposite of what we did. Every connection here needs to have an opposite contact, because these ones were leading to a logic 1. Remember, the one we did previously was leading to a logic 1 because this was negated. But now, because he's decided to use a normally open contact, we know that we need to achieve a logic 0. And to achieve a logic 0, we can decide that now we change the position of all this. We say that the proper condition that should be that this one should be now normally closed. But now, because we are having a logic 0, and now he has connected them in series, which is fine, it means the water level here was normally open, okay? But now, because we want a logic 0, it should be normally closed. So I think that is fine. This is fine. The oil pressure for logic 1 was normally closed. So now it should be normally open. Oil pressure should be normally open, but here I see that it is normally closed. So I think this is where the problem is. Let me check the others as well. Vibration, we said should be normally closed for a logic 1 shutdown, but now it's a logic 0 shutdown. So it should be normally open. Yeah, so that is now fine. The leak was a normally open for a logic 1 shutdown, but now it is a logic 0 shutdown, so it should be normally closed. So that is fine. So therefore, it means that now oil pressure ndio iko na shida, because it's supposed to be in the normally open position. Remember, for a logic 1 shutdown, it was meant to be in the normally closed position. So for a logic 0 shutdown, we need it to be in the normally open position. So this is where the problem is with the second attempt. So you can see again, even in your own use, you can either decide to connect these things in logical OR function, but you expect a logic 1 shutdown, or connect them in a logic AND function, but you expect a logic 0 shutdown. So it depends on your choice of the shutdown. Is it normally open contact or normally closed contact? That's your prerogative as the designer. All right, so I think that is fine. The second one has a problem with the oil pressure. It should be normally open for a logic 0 shutdown based on the physical device connection that we had discussed previously here. Okay, lastly, part C is the engineer's final attempt is shown. Does it contain an error? If yes, identify the error. So I see this is similar to what we've just done up here. The start button, the stop button, the shutdown is normally open still. The motor is latched properly. Okay. Second rung. Oil pressure, we said should be open. Now it is open here. So here it is in the correct position because we said it's supposed to be open, not closed. So oil pressure is in the proper position. Water level is in the closed position the way it was. So this is still fine. The leak is still fine by me. Vibration high, I see is still fine. Yeah, so this is now a proper circuit. You can take your time to simulate it if you want, but now this now becomes a proper circuit. It now can work. I only have one problem. No, the stop button. What was the condition of the stop button? It's in the normally closed position. Okay, so if the stop button is in the normally closed position, then here it's supposed to be normally open. So we have no problem. So I think for me that question 2C now solves the problem. One, the 2A had a problem with the vibration high contact. The second one had a problem with the oil pressure low contact. But the third one, I think now has no error. The beauty of these things is you can actually simulate them to see if they meet the conditions that have been asked. Okay, so ladies and gentlemen, my time is up. I see it's 4 minutes to the end of my time. We have how many questions to go? At least 3. Question 2, question 3, where the Vivo guy is designing their own simulator, a program for controlling some high pressure switches. And then question 4 should be very simple. Question 5 is for the water tank. Yeah, to design a PLC program for the water tank. Now, ladies and gentlemen, I intend to end my class on Wednesday. I don't want to extend it to next week. So perhaps because we have actually discussed this, I don't know if there's any specific problem. I don't know. Do you want us to do question 3? Question 4 is very simple. I can even send you the solution to this because this is easy. This is A plus B. This is C complement. So this is C complement plus D. So lastly, here we have A plus B and C complement plus D. So as your output. So Y should be AC complement plus AD plus BC complement plus BD. And so if you are to implement this using a logic diagram, actually you can even implement it here without opening, because opening it up will give you issues. You can implement it as that. Remember, A or B. This is like saying you have to write it in Boolean logic. Y, the output Y is equals to A or B and C complement or D, like that. And you know that this simply means that you have your logic diagram. A is just normally open contact, or B, meaning they're supposed to be in series. Okay, so A or B, like that. A or B. I can even put it like this. A or B. So they are in parallel. A or B. And C complement or D. So there is C complement. C complement, I can use a NOT gate. So C complement like that. So this, but you write C because you don't write C complement. If you write C complement and you use a NOT gate, then you mean C. So you write C and you use a normally closed contact. So this is C, not C complement. This is C. My time is up. So this is C, and then or D. So again, you have D like that. And you connect this to your output Y like that. So it is A or B, and so this is parallel combination for the first one. So this is A if A or B and C or D, then Y. Yeah. So basically what happens here is you just implement the C using a NOT gate, because a normally closed contact, because it is C complement. And so A or B and C complement or D. Now, again, you can tap this from here. You know, some people will be like, oh, now this is still rank 1. There's no rank 2 here because this is just branching out. So you can even tap it from here. I don't have a problem. It means the same thing to me. So basically what we have not done, because time is up, is question 3 and question 5. So maybe we'll quickly run through those in the next class and then we finish up. So let me see if there are any questions, ladies and gentlemen, or if you have to ask. Let me see if there are any questions on the chat. Again, I don't see any questions on the chat. Maybe I'll check with you whether it is question 3 that you want us to do, or question 5, or both. But either way, we will try and solve them in the next class so that we complete the tutorial. But at least now I appreciate that you understand some of these concepts and you can run with them, not just during the exams, but even later in your career. All right, I don't see any questions. I don't see any hands. So thank you guys very much. Let's have our class on Wednesday and complete the rest of the work. And then you can have time to get ready for your exams. Sawa sawa. So I'm waiting to see any hands. I don't see that.